Hello friends and welcome to a new video. Today let's talk about something every physics student come across, electron spin. We often hear that an electron has spin and we represent it using arrows like spin up and spin down. But what does the word spin actually mean? Does the electron really spin? Let's find out. What exactly is electron spin? The word spin immediately makes us imagine something rotating about an axis. But is that what an electron is actually doing? No. And understanding this is important because the word spin can easily make us apply the wrong classical picture to an electron. In classical physics, when an object rotates about an axis, it can possess angular momentum. So we naturally make the connection between rotation and angular momentum. If the rotating object is charged, its motion of charge can also produce a magnetic moment. This classical picture is useful for understanding why the word spin sounds so natural. But the electron is where things become very different. There's an interesting historical point here. The idea of a quantized spinning electron had actually been proposed earlier by Compton in 1921. Then, in 1925, Uhlenbeck and Gaudsmit independently proposed electron spin in connection with important features of atomic spectra. The important idea was that the electron appeared to possess an additional quantum property that behaved like angular momentum. This property came to be called spin. Initially, it was natural to imagine this using a familiar picture of a tiny rotating object. But that classical interpretation turned out not to be correct. So, why did physicists use the word spin? Because this new quantum property behaved in important ways like angular momentum. And the classical analogy with a rotating charged object made the name seem natural. But here is the key point. The word spin describes the behavior of this quantum property. It does not mean that the electron is literally rotating. This is the idea we need to keep throughout this video. So what happens if we insist on treating the electron as a tiny rotating sphere? The classical picture runs into serious problems. If we try to reproduce the electron's observed angular momentum and magnetic properties using such a model, the required rotational behavior becomes incompatible with relativity. In other words, the classical spinning ball picture cannot describe the electron correctly. So we have to let go of the idea of a tiny sphere physically rotating about an axis. Now comes the important question. If the electron isn't physically rotating, then where does its angular momentum come from? The answer is, it is intrinsic. Intrinsic simply means that the property belongs to the particle itself. The electron does not have to be orbiting the nucleus or physically rotating like a classical object spinning around itself in order to possess spin. Spin is a fundamental quantum property of the electron. A useful way to think about this is to compare spin with another property of the electron. Say electric charge. The electron has charge because charge is one of its fundamental properties. We do not ask what the electron is doing in order to produce its charge. Similarly, spin is a property that the electron possesses intrinsically. So, the simplest way to say it is, spin is intrinsic quantum angular momentum, but it is not mechanical rotation. Now, let us distinguish two ideas that are often mixed together. An electron can have orbital angular momentum, generally represented by L, which is associated with its spatial motion. And it can have spin angular momentum represented by S, which is intrinsic to the electron. So, the electron can have two different forms of angular momentum in quantum mechanics, and spin does not require the electron to move around. So, if spin is not caused by rotation, why do we call it angular momentum? Because spin follows the quantum rules of angular momentum, as in it can combine with orbital angular momentum, it interacts with magnetic field, and most important for us here, its measurable components are quantized. So, we can think of spin as an intrinsic quantum property that behaves like angular momentum even though it does not originate from physical rotation. Now, let us see what this quantization actually means. For an electron, the spin quantum number is s equals to 1 by 2. It is a quantum number that characterizes the electron's intrinsic spin. And from this quantum number, quantum mechanics tells us what values the spin angular momentum can have. The magnitude of the spin angular momentum is root over s into s plus 1 h cross. For an electron where s is equals to half, we get the magnitude as square root of 3 by 2 h cross. But when we make a measurement, we usually measure a particular component of spin. For example, let us choose a direction z. For an electron, the result can only be Sz equals to plus h cross by 2 or minus h cross by 2. So, the measurement is quantized. We do not get any arbitrary continuous value. These two outcomes are conventionally called spin up and spin down. And notice something important. Up and down refer to the chosen measurement direction. They do not mean that the electron is literally pointing upward or downward in space. So, what does the familiar arrow means? When we write up arrow or down arrow, we are using a simple notation to represent the two spin states. Up arrow could correspond to h cross by 2 plus h cross by 2, while down arrow can represent minus h cross by 2. The arrow is therefore part of our quantum description. It is not a picture of electron physically pointing upward or downward, and it is certainly not showing the direction in which the electron is rotating. So, when you see a spin arrow, think of it as a label for a quantum state, not as a tiny arrow attached to the electron. And now, we can connect this back to Pauli's exclusion principle. Spin gives the electron an additional quantum degree of freedom. Therefore, two electrons can have the same spatial state while having different spin states. So, when we describe the complete quantum state of an electron, we need to consider not only its spatial state, but also its spin state. And that is why spin becomes so important in understanding Pauli's exclusion principle. So, what should we remember from this video? First, an electron has spin, but spin does not mean that the electron is literally spinning or there is any physical rotation involved. Second, spin is an intrinsic quantum property associated with intrinsic angular momentum. Third, for an electron, there is no arrow pointing up or down, and when we measure a component of its spin along a chosen axis, we obtain quantized outcome. So, the next time you hear the statement, the electron has spin, don't imagine a tiny ball rotating in space. Think instead, an electron possesses an intrinsic quantum property that behaves like angular momentum, and that property is what we call spin. Thank you.